Okay, so 1.
See, now that was mean. So right, one is an epsilon. Well, no, because epsilon has to be less than or equal to half. We already said that. But you're right. In a sense, setting epsilon to 1 is always a valid answer to the question. Find an epsilon such that we've epsilon exhausted the version space, because all it's saying is that there's nothing left in the set that has an error greater than 1, and since the error is defined to be the probability, it can't be greater than 1. So that was kind of kind of rude.
I don't know. I thought I just answered the question, but I
You
guess
did,
you want me to give you.
what you probably should have pointed out is that I left out the word smallest.
Ah, yes, yes. Okay. Well, so I don't know the answer to that, but I think I could walk through it very quickly.
Okay.
Okay. So you're saying the ones that are in green are the training examples that we see, right?
Right.
So we should be able to use that to figure out what the version space actually is.
Right, which we did in a previous question.
Right. Although I don't remember
Here,
what
I'll
the
remind
answer
you. It's
was.
okay. So it was
Okay.
x1,
Mm-hmm.
right, because the x1 matches. It was OR and XOR.
Mm-hmm.
I think that was it.
Yeah, I think that's right. Okay, so then what we can do is, given that those are the three things that we've done, we could actually compute what the error is according to this distribution for each of those three.
Yes, exactly so.
So let's start with x1. So
Okay.
which one? So x1. So all three of those are going to get the first one and the third one correct, right?
All of them are going to get the first one and the third one correct. Yes, by design, right?
By
Because
design.
that's to be in the version space.
So now we can ask which ones will get the second one wrong. The fourth one doesn't matter because it has zero probability of showing up.
That's right. So it doesn't matter if you get this one right or wrong. It's not going to contribute to this true error measure.
Okay, so let's look at x1. So x1 will in fact get the second one wrong because the output is not the same as the value for x1.
Good. And so what's the probability that x1, this hypothesis x1, is going to give a wrong answer on a randomly drawn input?
Well, half the time it will get the second answer, and so the error is in fact 1/2.
Yes, exactly. Good. All right, let's move on to the OR.
Okay, well, we can do an easy one actually. We can do XOR. Since we know XOR is the right answer, we know it will has a probability of being wrong of 0.
Oh, good point.
Okay, and so for OR we can do the same thing. So we know it's going to get the first and the third ones right. So now we can ask whether it's going to get the second one right. And 0 or 1 is in fact true, or 1. So in fact it also has an error of 0,
Okay.
which is kind of interesting. So even though the function is XOR, if we can get to the point where we have OR or XOR left, we actually will get 0 true error.
That's right.
But in the meantime, because x1 has still survived the two examples that we have, epsilon is therefore 0.5.
Right. In particular, we're saying that this is if epsilon were smaller than 0.5, then it wouldn't be epsilon exhausted because you'd have a hypothesis that has error that's too high. So this
Right.
is the smallest epsilon that we can use. And in fact, we let you through if it was anything 0.5 to 1, but this is the value that I was really hoping you'd be able to reason out.
Okay. Well, that all made sense.
Good. Nice work.
Thanks.